National Electrical Code, or NEC, dictates the requirements for neutral conductor sizing in a grounded neutral system. NEC Section 215.2 A4 specifies that the neutral conductor must be sized based on the maximum imbalance of the load. For a 3-wire, single-phase circuit, the neutral conductor shall have an ampacity of not less than the maximum imbalance of the load. For a 4-wire, 3-phase circuit, the neutral conductor shall have an ampacity of not less than twice the maximum imbalance of the load. To determine the maximum imbalance of the load, utilize this formula: maximum imbalance equals the maximum load on any one phase minus the minimum load on any one phase. It is vital to accurately calculate this imbalance to ensure the neutral conductor can safely carry the expected current. Insufficient neutral conductor sizing can lead to overheating, voltage drop, and potentially hazardous conditions. Moving on to grounding, NEC Section 250.112 mandates a continuous electrical path to ground for all grounded conductors and equipment within an electrical system. This continuous path must be established using a grounding electrode conductor, or GEC, which connects the grounding electrode system to the electrical system. The grounding electrode system typically consists of a grounding electrode, such as a ground rod, metal water pipe, or concrete encased electrode, and the necessary bonding connections. The GEC ensures that fault current has a low impedance path back to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. NEC Section 250.112 C further stipulates that the GEC must be sized based on the ampacity of the overcurrent device protecting the circuit. This sizing is crucial to ensure the GEC can safely handle the fault current without overheating or becoming damaged. In situations where there is no dedicated GEC between a lighting distribution panel and the end panel, this violates NEC Section 250.112 C. The absence of a dedicated ground conductor compromises the safety of the electrical system and increases the risk of electrical shock. Using heat shrink to designate a conductor as a neutral conductor is not an acceptable practice according to the NEC. The neutral conductor must be clearly identified with white or grey insulation throughout its entire length. This consistent color coding ensures that electricians and other qualified personnel can readily identify the neutral conductor, reducing the likelihood of wiring errors. Furthermore, the NEC prohibits the use of non-compliant cables. All cables used must be listed and labeled by a nationally recognized testing laboratory, or NRTL, like Underwriters Laboratories or ETL Semco. These NRTLs rigorously test and certify electrical products to ensure they meet established safety standards. The listing and labeling indicate that the cable has been evaluated and found to be safe for its intended use. Utilizing non-compliant cables can introduce significant safety hazards, including fire risks and electrical shock potential. It's crucial to adhere to NEC regulations regarding cable selection to maintain a safe electrical system. Given the complexities of electrical systems and code compliance, it is highly recommended to involve a qualified electrical engineer. A qualified electrical engineer can thoroughly assess the electrical system, identify potential code violations, and provide recommendations for corrective actions. They possess the expertise to ensure that the electrical system meets all applicable NEC requirements and operates safely and reliably. Their involvement can help mitigate risks and prevent costly mistakes. To further elaborate on neutral conductor sizing, it's important to understand the concept of unbalanced load in a three-phase system. An unbalanced load occurs when the current flowing through each of the three-phase conductors is not equal. This imbalance can result from differences in the loads connected to each phase. For instance, if one phase is heavily loaded with lighting while another phase has minimal load, this creates an unbalanced condition. In a balanced three-phase system, the neutral conductor theoretically carries little to no current because the currents in the three phases cancel each other out. However, in an unbalanced system, the neutral conductor carries the difference in current between the phases. Therefore, the neutral conductor must be sized to handle this unbalanced current without overheating. The NEC provides specific guidelines for calculating the minimum ampacity of the neutral conductor based on the expected maximum unbalanced load. These guidelines take into account factors such as the type of loads connected to the system, the presence of nonlinear loads, and the potential for future load growth. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents that further increase the current flowing through the neutral conductor. As a result, it may be necessary to oversize the neutral conductor to accommodate these harmonic currents. In addition to ampacity, the neutral conductor must also be sized to minimize voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can negatively impact the performance of electrical equipment and lead to malfunctions. The NEC provides recommendations for maximum allowable voltage drop in branch circuits and feeders. To minimize voltage drop, it may be necessary to increase the size of the neutral conductor or reduce the length of the circuit. Proper grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly trip and de-energize the circuit. Without proper grounding, fault current can flow through unintended paths such as building steel or plumbing, creating a shock hazard. The grounding electrode system, consisting of a grounding electrode and a grounding electrode conductor, establishes a connection between the electrical system and the earth. The grounding electrode provides a reference point for voltage and helps to stabilize the voltage during transient events such as lightning strikes. The grounding electrode conductor connects the grounding electrode to the electrical equipment and the neutral conductor at the server's entrance. This connection ensures that the electrical system is effectively grounded and that fault current can flow safely back to the source. In addition to the grounding electrode system, equipment grounding conductors, or ECs, are used to ground non-current carrying metal parts of electrical equipment. EGC provide a low impedance path for fault current to return to the source in the event of a fault. EGC are typically run with circuit conductors and connected to the equipment grounding terminals. The NEC requires that EGC be sized based on the ampacity of the overcurrent device protecting the circuit. The NEC also specifies the types of wiring methods that are permitted for use as EGC. These wiring methods include metal conduit, metal raceways, and bare or insulated copper conductors. The use of heat shrink to identify a conductor as a neutral is a common but improper practice. The NEC mandates that the neutral conductor be readily distinguishable from other conductors by its consistent white or gray insulation. This standardization aids in quick identification and minimizes the risk of accidental miswiring. The consistent color coding of the neutral conductor ensures that electricians can easily recognize it and make proper connections, reducing the likelihood of errors. When selecting cables for electrical installations, it is crucial to ensure they meet the NEC requirements and are listed and labeled by a nationally recognized testing laboratory, or NRTL. NRTLs rigorously test and certify electrical products to ensure they meet established safety standards. The listing and labeling indicate that the cable has been evaluated and found to be safe for its intended use. Cables that do not meet these requirements may pose a fire hazard or electrical shock risk. The NEC provides specific requirements for the types of cables that are permitted for use in different applications. These requirements take into account factors such as the voltage rating of the cable, the ampacity of the cable, and the environmental conditions in which the cable will be installed. It is essential to select cables that are appropriate for the specific application and that meet all applicable NEC requirements. Employing a qualified electrical engineer is highly recommended to ensure electrical systems comply with all applicable NEC requirements. Electrical engineers possess the knowledge and expertise to design, install, and maintain electrical systems that are safe and reliable. They can conduct thorough inspections, identify potential code violations, and recommend corrective actions. Their involvement can help mitigate risks and prevent costly mistakes. Electrical engineers are also familiar with the latest NEC revisions and can ensure that electrical systems are designed and installed in accordance with the most current standards. Their expertise is invaluable in ensuring the safety and functionality of electrical systems. To summarize the key points, firstly, the neutral conductor in a grounded neutral system must be sized based on the maximum unbalanced load as per NEC section 215.2 A4. Secondly, a continuous electrical path to ground is mandatory for all grounded conductors and equipment established through a grounding electrode conductor, or GEC, as per NEC section 250.112. Thirdly, the GEC must be sized according to the ampacity of the overcurrent device protecting the circuit, in compliance with NEC section 250.112. D. Fourthly, using heat shrink to designate a conductor as a neutral is not acceptable. The neutral conductor must have consistent white or grey insulation. Fifthly, only cables listed and labelled by a nationally recognized testing laboratory, or NRTL, should be used. And sixthly, involving a qualified electrical engineer is recommended to ensure NEC compliance.